Let's talk about concave lenses. Concave lenses are thin in the middle and thicker at the edges. I've drawn an example here. Notice that the curvature is such that it is kind of like a cave, hence the name. Now, we're going to assume that this lens is made of a material such as acrylic or glass, something that has greater density than air and causes the light to refract when moving through it. So let's imagine that we have a source of light on the left-hand side. I'm going to draw some representative rays. Trying to get this to be at 90 degrees to that center line. I'm going to draw an arrow to indicate the direction of the light ray. Now, I'm going to draw a couple of rays fairly equal in distance away from one another. I'm going to try to draw this symmetric around the optical axis. Okay, I'm not going to draw a line along the optical axis, but I am going to imagine there is a ray of light along that center point. So we can first ask ourselves what's going to happen to the ray of light that's going through the very center. If we look at the curvature of the lens at that optical axis right there in the middle, there's going to be a tangent to that curvature that is completely vertical. That is to say, when we have a ray of light that comes in along the optical axis or striking directly in the middle, it's going to pass straight through. And so we imagine that this line is going straight through without being changed in its trajectory. Now, what's going to happen to some of the other rays? Well, what we're going to see is a refraction that brings light rays outwards like this. So here's the first one. Well, let me try and remove that little dot. Okay, so let's take this first ray, and we're going to have refraction like this. If we look at then the top ray, we're going to have refraction like that. And we're going to have a very similar situation on the other side here. So what's going on here with these rays of light? Well, they are, with respect to one another, diverging. And so in fact, this is another name for this type of lens. Concave lenses are also known as diverging lenses. So I'm just going to make a note of that. Okay, so last time when we looked at convex lenses or converging lenses, we saw that the light converged to a point which was an important defining characteristic for that lens, and that was the focal point. how do we define a focal point for a diverging lens? Well, what we're going to do is trace back those refracted rays. And if we do this, we end up getting convergence on what we will then describe as the focal point. Okay, so now we have a way of finding the focal point and thus the focal length of this type of lens. So I'm just going to make a note that this is our focal point, and there is one on either side at an equal distance. We can measure this if we did it in the lab, or if you have a ruler and do this on paper. If we do that in this case, we find that this F value is equal to 3 centimeters. Now, we can use the focal length in the same way as a convex lens to describe how strong that lens is. That's going to be dependent on the material that the lens is made of. If we make it out of something with greater density, with a larger index of refraction, we'll have more divergence between those light rays. They'll bend more. Alternatively, we can change the curvature. So the curvature of this lens will also affect the strength and how much we have this divergence. So that's our introduction to concave or diverging lenses. This is how they're defined and how we can find the focal point. I'm just going to make a little note of the focal distance or the focal length. Maybe what I'll do is I will move this down there. Okay, next we will take a look at this type of lens and image formation.